Thanksgiving. All right, up. All right, let's go. Chris was going to come in today. He's the one who wrote the exam scheduling algorithm and is still working on it. But he got the flu and is sick, so he's going to come on Friday, just give about 20 minutes then. Yeah. What? Nope. I have no idea when the exam is. I don't find out any earlier than you, so I know it's frustrating. He
said, is he going to tell us?
Yes, no, and I said, no, he's not going to tell us when the exam is. He just runs the program. He doesn't. He just wrote the program that schedules exams. I'm sure it's all very political. Sorry? I have no idea. Not me. Someone in the... I don't know. That's a good question, though. I don't know when we do it. Assignment due in one. Assignment 2 is due in 1 week. Has people started? Okay, good. And the midterm is in the week after the election. And is there any other questions? Okay. Okay, so what we've done so far in constraint satisfaction is we've defined constraint satisfaction in terms of variables, domains, and constraints. And we've had 3 ways of solving them with searching assignments of values to variables, arc consistency with domain splitting, and local search. And local search, the main idea is it maintains a complete assignment of a value to every variable, and you have a mix of improving steps and randomizing steps. So if you imagine assigning courses to exams, right? We just start with some random assignment, and then we keep iteratively improving it, but sometimes we do randomizing steps as well. Okay, are there any questions about that? Someone asked me to explain a bit more about runtime distributions. So here's a bit more about the runtime distribution. As what we do is we run the same, when we see these runtime algorithms, we run the same algorithm on the same instance for a number of trials, for example, 100 or 1,000. So all these distributions, the ones we're doing are looking at what's the distribution of this algorithm on this instance. You can imagine one algorithm on multiple different instances or all sorts of things. But in what we're doing is we're running the same algorithm on the same instance a number of times. Because each of them are randomized, we end up with a distribution over them. Then we sort the trials according to the runtime. So then we just sort them. So we just sort them. And then what we're going to do is that we're going to plot on the x-axis the runtime for the trial, on the y-axis the index of the trial. So we're just going to effectively sort them according to the runtime, and that's going to give us this cumulative distribution. We can do it as a few times to gauge the variability of it, and if you want to study variability, the subject is called statistics, and I'm not going to explain it, but I'm not going to go through it because it would take me too long, but if you want to understand how these vary, it's how it's statistics. And sometimes we're going to use the number of steps instead of the runtime because computers run small runtimes inaccurately. And however, running with the number of steps is not a good measure if the different steps take different times. So let's show an example of this. Let's show. So this is for, we're going to pick a random node, and we're going to check the best value 100% of the time. So that's what we're going to do here. And we're going to do a batch run. We're going to do 1,000 of them. We're just going to run it. We're just going to run it, and if you notice, when we just run it, and we get the individual steps, and then we just sort them, right? And I've run it the previous times, and if you notice 1,000 times gives a pretty good curve. So if I run it a few times, it's going to be pretty accurate. It's going to be pretty similar to the previous times. So if I run it again, the same algorithm, it's going to be pretty. I'm just going to run each one of them. Here I'm displaying each of them, then I'm going to sort them, and it's going to be a very similar algorithm. And if I change the algorithm, there's a few other points you want to make here. If you change the algorithm to always choose the best node, never to choose that. I run this again. The thing that's interesting about this is it often takes the maximum amount of time. Okay, but often it takes less time. So some of the times it can solve it in much fewer steps. Okay, and if I want to do something better than this, what could I do? So if I wanted to do something better than this bottom one in terms of the number of steps, notice this is pretty good up to about 15 steps, but it's actually really good up to about 7 or 8 steps. It's really good, right? But what I could do is I could do something else. I could do a random restart after this. Oh, random. So I could do a random restart of about 8 steps. So I'm just going to random restart. I'm going to random restart after 8 steps. And if I do this, what do you think will happen? It's going to repeat the green one for the first 8 steps. I think it's going to keep doing it again. And we find out that it's better than the previous ones. However, it's sort of not really better. Why isn't it really better than the other ones? In terms of, here notice we're doing the number of steps. What's wrong with the random restart? Right, it's sort of, if you have lots of variables, random restart's really slow because you have to visit every variable, right? But these other steps that are very local, you just pick a variable and then you can just change the value for one variable. So although something like this has much fewer steps, if we plot runtime, which I think we can draw times here, that black thing, because it's too fast, my computer's too fast. Okay. Everything takes either 0 or no milliseconds. You need to get a really old computer to do this size algorithm on times. Okay, any questions about that? Yes? What? Which algorithm? The running time for plotting. To do a random, actually we'll talk about that. That's next. We'll talk about that in a minute. Okay. All right, let's go back to here. All right, so let's do some clicker questions. If there are other questions. Let's go this. I like which of the following is false? Choosing values at random allows a local search algorithm to escape from local minima. B, a random walk will eventually find a solution if there is one. C, greedy descent will eventually find a solution if there is one. Or D, adding a random walk will often make greedy descent more efficient. So which one of these is false? Oh, what's going? Rate of change. Anyone need more time? Anyone need more time? A few people. Do you still need more time? Okay, let's stop. 3, 2, 1, I'm stopping. Oh. It moves. All right. C is the right answer. A few people said B. Random walk will eventually find a solution is true. If you just assign things randomly, it eventually finds a solution just by randomly. Might take a long time. And adding a random walk to greedy descent often makes it more efficient. So if I added a random walk to this other one, if I added a random walk to the algorithm, I won't do that. If I had a random walk to the algorithm for that just greedily chooses the best node, it will eventually solve all of the problems. Okay, any questions? All right, let's do this one. This question is about what happens if there's no solution. Which of the following is true? Greedy descent and random walk can quickly determine if there is no solution. B, greedy descent is better than random walk if there's no solution. C, random walk is better than greedy descent if there's no solution. Or D, neither greedy descent nor random walk work if there is no solution. Oh, you can read. I can't pronounce, but you can read. All right, do you need more time? Who needs more time? 3, 2, 1, I'm stopping. Moves. All right. The answer is D. If there's no solution, it just goes on forever, both of them. Right, if there's no solution to these problems, they just keep assigning values because it doesn't stop. Few people said B, greedy descent is better than. No, it's just if there's no solution, it just keeps going forever. You just keep changing values and it doesn't stop. Okay, because it just stops when it finds a solution. Or you've run out of timeout. Any questions about that? All right, here's the one. Last one for the day. Which of the following is true? A, as all step sizes take the same amount of time, comparing algorithms or settings according to the number of steps is just as good as comparing run times. B, it's better to compare with run times as there is more difficult with simple, but that is more difficult with simple problems with short run times. C, it doesn't matter what search method is used because it's all random anyway. D, any algorithm is as good as any other because any could guess the right answer initially. Or E, all of the above. How are we going? All right, we're stopping. B, good. You should do that. That's what we just did. A few people said A. This is just. Some things are expensive and some things are not expensive. Some of these steps are very quick and some of them are not very quick. Okay, any questions about that? All right. So what we're going to do today is at the end of the class we're going to explain the trade-offs between sort of step size and speed. We're going to look at a bit of something called taboo search. And then we're going to look at some population-based methods that can improve local search. So the local search that we have so far is we just maintain a complete assignment of a value to a variable. We're going to start with a random assignment for a good guess. We're going to repeatedly do this, selecting a variable, and selecting a value until we find some satisfying assignment. And all the algorithms really differ in this by how we select the variable and how we select the value. So let's start looking at a few ways of doing this. So the first way to do this is we could select a variable value pair that minimizes the number of conflicts. And if we do that in this algorithm, if we do that here, that's one of the options here. Oh, algorithm options. We're going to choose the variable and the value. We're going to choose it 100%, and I'm not going to re-step it. And if we do this, and we do a batch run of this, we're going to find out that it's actually, that has some, so we'll find that, well, let's see what it does. You find that it's actually much better. This previous green one down here, this one in the middle here, see this one there in the middle, was choosing the value, that variable, then the value. This one was choosing the variable, choosing the best variable value pair. Okay? And if you run it, and if you try and do it with a, what's this point here? And if you try and do it with a random restart of up to 6 or 7, we can get a really good algorithm. Let's do this. Let's do a random restart after 6 or 7. Restart after 7, let's do 7 steps. And we'll do a batch run of this, and we'll find that it's that this seems like a really good algorithm, right? It's much, much better than any of the other ones, right? This is a really good algorithm. Okay. It's the best algorithm we could possibly do, except, where are we? Okay, so this is a really good algorithm. However, what data structures do we require? In terms of number of steps, what data structures do we require to do? So we choose the best, let's say the best variable value pair. What data structures do we need? What do we need to do this, to implement this? How do we choose the best of some things? Yeah. A priority queue on what? Queue on the variable value pairs, right? And what also happens with this algorithm is that when do we update it? We don't only select the best one, we also have to keep if some variable changes. So if we have a variable here, and an assignment, another variable, another thing here, right? And this changes. That's the red. This changes. And suppose this changes. What do we have to update? Yeah, we have to update all these neighbors. Right? So this requires not only updating this, but it requires updating all of these neighbors. Right? So it actually requires, so this requires, not only do we have to, in the priority queue, pop the best one off, we have to also update all the neighbors. Right? So each step requires updating. So this is the data structure. And this requires you have to the update all the neighboring variables. Okay? So one step in this priority queue, and priority queues, remember, aren't really designed for updating neighboring variables. Yeah. We can do all sorts of, I'm actually not going to. You can do a heap, you can do a binary search tree. You can do what the Python manual tells you to do is just to keep an index of these ones and just mark them as deleted, and when you pop them off, you empirically what works best is you keep a normal heap, but you just mark these as deleted, and when you pop them off a deleted one, you just throw them away. It turns out that's actually more efficient than getting one of these and shuffling it down or up. Right? As this changes, you have to shuffle this down or up. And it's very expensive. Right? So this is actually very expensive to do this. Okay, so you have to do this. It turns out it's proportional to the number of varying neighbors. And for each of these, you have to either shuffle them up or down in this priority queue, or you have to mark them as deleted and reinsert them. Okay, so although this is a really fast algorithm in terms of number of steps, it's a complicated data structure, and there's lots of work you have to do for every step. Okay, let's look at another one. We're going to select the variable that participates in the most conflicts, and then we're going to select the value that minimizes the number of conflicts. Does that make sense? So that's the one that we've been doing mostly. And on that algorithm, it didn't work nearly as well as the first one, but so what data structures do we need? So this is the best variable. Then the best value. So what data structure do we need in here? What do we need just here? How do you select the best of something, the best? Right, what do we do here? What data structure do you need to select the best thing? What do we do before to select the best thing? You need a priority queue with what? On what? Yeah, you need a priority queue on variables. Queue on variables. Right, so the priority queue here is a lot smaller. Right, this priority queue is a lot smaller than this priority queue, because this is all variable value pairs. This is a much smaller priority queue. And now what we're going to do is the neighbors, we still have to update this, because now we only have to do the neighbors, which if this became a conflict. So if this became a conflict, you have to update this. But if it didn't change, we don't have to change it. Okay, so we only need here the neighboring variables, which are connected to conflicts, connected to constraints that change from true to false. So the only ones, in this one, the first one, we actually, even if this didn't change, it could be the case that you have to change this variable. In this case here, we only have to look at the ones that change. If this one changes, we have to update this. If it doesn't change, the number of conflicts for this doesn't change. Right, but if this becomes a conflict or stops becoming a conflict, you have to update this variable, because the number of conflicts it participates in has changed. Yes?
Why would you only have to check the constraints that change from true to false? Because it's possible that by minimizing the number of conflicts, you might change many of those from true to false, but you might also change something from false to true to create a conflict if you're minimizing the number of conflicts.
Right, so when this changes, there's going to be a certain number of this one might stay the same. Then the number of conflicts for this doesn't change. If this one changes, if this changes from either true to false or false to true, then then the number of conflicts of this changes. Right, so if this doesn't change, the number of conflicts here doesn't change. But if this changes, this number of conflicts of this one changes. Right? It doesn't matter whether it changes to true or false, we still have to reset this one. And if this one doesn't change, we don't have to check this. Right, so we only have to, because we're only checking the number of conflicts, it's actually much simpler than the first one. Right, so although this one seems like, if you plot the number of steps, it seems like a really good algorithm. No one ever uses it. It's a real, the data, maintaining all these data structures is so complex that when you actually plot the runtime, it's much slower. In terms of number of steps, it's better, but in runtime, it's much worse than this one. Okay. All right, let's have a look at another one. Oh, we did that. We select, but then you have to check, once we've selected a variable, they have to go iterate through the values as well. The other one we could do is select the variable that appears in any conflict and select the value that minimizes the number of conflicts. So this is any variable in a conflict. Right, then the best value. What data structure do we need in here? What data structure? You don't have to choose the best of anything. We just need a... Yeah, we actually just need a set of... We just need some set of variables that are in a conflict. And we still have to update. If this one changes, we have to update some of these ones. Right? If this one became a conflict, we have to add in all of the variables. If this became not a conflict, we have to do something more complicated. But it turns out this is much, and priority sets of values are designed to add and remove variable values to them, whereas priority queues are not designed to add elements to them and pop off the top element, not to change values. So again, this is simpler to implement, and it can be faster. Okay? So all the time we're going to look for, this is going to be fewer steps, but bigger steps. They're better. And this one's going to be smaller steps. We can do them fast. And then we're going to select the variable at random and select the value that minimizes the number of conflicts. So we select any variable, select a variable at random. Then we're going to select the best value. What data structures do we have to maintain? Right, well, we don't have to store anything. We can do this with no data structures. Here we had very complicated data structures that we had to maintain and update. And here we don't keep any data structures. We can do this really fast. Right, we might have to loop through the values. Okay? We might have to loop through the values to do this. And there's another algorithm we might even do that's even simpler than that, is select the variable and the value at random and accept the change if it doesn't increase the number of conflicts. Right? So we select the variable and value at random and value at random. And this is even faster than this because this requires looping through the values. And this one doesn't require looping through the values. So it's going to select one and then either accept it or reject it. So as you go down here, as we move down here, right, the algorithms get simpler, but we're sort of essentially taking smaller steps. So if you go down this list here, I've run out of room. As we go down here, in some sense, we take smaller and cheaper steps. Smaller and cheaper steps. Okay, and as we go up there, we're going to take more expensive steps because they require all these data structures. But the steps are going to be essentially bigger. So one of these we're taking very big, slow steps, and the other one we're taking lots of little steps. Right? And just by studying the complexity of this isn't going to tell you what's going to win. Right? We actually have to run these algorithms and test what's going to win. Okay, questions about that? Okay. All right. Any questions about that? So, yes.
Go over again what happens in an update when you have
So when you have any variable, if this changes its value, if this becomes a conflict, when it wasn't a conflict, all of its neighbors get added to the set of conflicts. If this became not a conflict, we have to go through all the variables and we have to see whether they're in another conflict. Right? You could actually store all the conflicts you could store this big indexing of which conflicts these variables are in. So you can index them so this variable can be done fast, or you could just go through all of the constraints that they're in, participate in. And whether it's worthwhile doing the index or not, we don't know. If there's only a few conflicts that they're involved in, it might be just better just to go through each variable and see if it's a conflict. Does that make sense? Because what we should be able to do, what I want people to do is to get in this way of thinking about algorithms just by sort of going through the idea about algorithms, and then we can sort of discuss how they work. Any other questions about this? All right. So one of the measures, when we have an assignment, one way to measure them is just the number of conflicts. And it's possible to weight some of the conflicts higher than other conflicts. So one of the things we might think about is, well, maybe we don't want to weight all of these with weight 1. Maybe we could weight them with weight 2. So why might we? Well, the answer is because some of them are easier to solve. So in scheduling exams, it might be the case that there are some conflicts that are really hard to resolve, but once you have the times for the exams, then maybe the rooms are actually easy to get. Right, so maybe we want to assign all of the times for the big exams first and have that as a big weight, and other ones have smaller weights. So when we do this, so when Chris talks on Friday about his exam scheduling, I think he's going to talk about how there are different weightings for associating with which is the best. So instead of having just the number of conflicts, we're going to have these weighted conflicts. And if n's a total assignment, we're going to define h of n to be some measure of the difficulty of solving this problem from assignment n, and it deliberately looks like the heuristic function. It's our guess about how hard it is to solve this problem. Right, so and if we can start improving this a lot more, we can start taking big steps, and we can start improving this a lot. And if h of n is 0, then we have a solution, and we prefer lower h's. Okay, so we're going to try and reweight these in some times. Okay? So yep, all right. So here's a very common variant that people do called simulated annealing. It was the physicists often talk about simulated annealing. So it's a local search algorithm. We're going to pick a variable at random and a value at random. And if it's an improvement, we're going to accept it. But we like to do some randomness, right? We like randomness. Randomness is good because it helps us escape local minima. So if it isn't an improvement, we're going to accept it probabilistically, depending on some temperature parameter. And if you're a physicist, temperature means high temperature is very random and low temperature is not random. So we're going to have this randomness. So this temperature, we're going to accept it with probability E of the difference between the temperatures divided by E of the difference between the heuristic functions divided by T. And so h of n is the evaluation. So we're going to have this temperature. As the temperature is high, we're going to be more random. And as temperature is low, we're going to be more random. So as temperature is low, we're going to be less random. And apparently this is how, it's called annealing, because this is how you get metals to be hard. You cool them down really slowly so they get to a low energy state. If you cool down metal or steel fast, then it becomes much more brittle. If you cool it down very slowly, it can reach this low energy state, which is very strong. So that's what annealing is in metallurgy. And we're going to reduce this temperature. And we can look at this. So here are some values for the temperature. If the temperature is 10, then if it's 1 worse, we're going to accept it 91% of the time. If it's 2 worse, we're going to accept it 81% of the time. And if it's 3 worse, we're going to accept it 74% of the time. So if its temperature is 10, we're sort of going to nearly accept every change, but we have a preference for, because we can accept every improvement, so we're going to have a slight preference for an improving step, and then as they get more and more worse, we're going to accept them with a lower probability. If the temperature is 1, where there's a 1/3 chance that we're going to accept the one worse, there's a 14% chance we're going to accept a 2 worse, and there's only a 5% chance we're going to accept some change that's 3 worse. So this temperature of 1 is going to sort of, we're really going to accept, we're going to have to make some downward steps, but we're unlikely to make a big downward step. Okay, and as the temperature gets down to 0.1, we're unlikely to make any changes. And so what these people do in these algorithms is they start off with a high temperature, and they reduce, so it's very random, and it's going to try to walk through this space, and then we're going to, and as it reduces, it starts just going just pure greedy descent. Right, so at 0.1, it might as well be greedy descent. So it's very unlikely you're going to take a lowering step. Okay, it's nice because it effectively has no data structures, but then, and you can sort of guarantee that it works. So it's often used for things where they're very high, where there are lots of values to these variables, and they're enormous problems. Okay, so this is one instance at the other end of this. Okay, does that make sense? Okay. Another idea that we could do. So that's one. Today we're just finishing up this local search. I'm just going to throw out a whole lot of ideas that people do. So to prevent, the other idea we could do is to prevent cycling, we can introduce something called a taboo list of the k last assignments. And we don't allow an assignment that's in the taboo list. So we're not going to allow you to repeat. It's a sort of it's a cheap cycle check, but it's only the last few steps. We're not going to have a complete cycle check. Or we could have a complete cycle check. So if your k is 1, you just don't allow the same value to change again. So you have to pick a new value to a variable. If it's 2, you aren't allowed to make 2 cycles. You're not allowed to go back to the previous one, but you can go back to other ones. And you don't need, because if k is small, you can actually implement it quite efficiently. Right? For k is small, you have to record just which variables changed. And then if you're only maintaining k as 2, you only need the last 2 values that changed, and you can check that quickly, of whether you're going back to that previous assignment. However, it's expensive if k is large, and taboo lists are often used mixing up these algorithms with a taboo list. It's expensive, but it lets you escape some sort of local minima that have small number of variables in them. Okay, that makes sense? Just remember the last few steps and don't go back. Simple. Okay? All right, here's some other ones. All right, when you have domains are small or unordered, which we've done, the neighbors can be just choosing any values for one of the variables. If the domains are large and ordered, so if you have if the domains are every integer from 1 to 1,000,000, or every time slot or something, the neighbors could be just adjacent values, so you can move to left or right if you have a big ordered domain. And if the domains are continuous, this doesn't work. You can do what's called gradient descent. And in gradient descent, if you have your domain is, you could view it in 1 dimensions. You could have, in gradient descent, what we could do, if you have a continuous domain, what you'd like to do is you'd like to move downhill. Now, who knows calculus? Who knows calculus? Who doesn't know calculus? A few people. All right. So what we do in here is we have some particular value for it. Calculus does the slope, and if the slope is negative, it's downhill. So we just take a step in the derivative. So in here, we just take a step downhill. And if we get to this point down here where the slope is less, we take a small step. So all the time we're just taking a step downhill. Any point we're at, we're going to take a step according to the derivative. If you don't know what calculus is, don't worry. If you know what calculus is, you're just going to take the derivative and take a step downhill. And the value of the variable goes from the value vi to the value minus some step size times the derivative. This doesn't make any sense to you, don't worry. But if it does make sense to you, then this is how neural networks work. They just have this huge number of real valued parameter spaces, and you walk downhill in this space. So neural networks effectively have this continuous space of real valued parameters, and it tries to minimize it to fit the data. But I'm not going to talk about that. You'll learn about that if you do 340. And so a lot of 340 is about this local searches with parameter spaces to try to minimize them. But it's very similar to what we've done. All right, a few more ideas that people do. So one of the things we could do is to think about modeling it as having a total assignments sometimes we call total assignments called individual. And they call that because we have a population of individuals. So sometimes you're going to run a whole lot of these gradient descent searches in parallel. So we're going to maintain a population of k individuals instead of one. So before we just had one thing we're moving down. Now we're going to have k different values we're all going to try and move in different places. And at every stage we're going to update every individual in the population. And whenever one of these instances finds a solution, it can be reported. So it's going to be like restarting at k times, except it's going to be k times the minimum number of steps. Just going to do k things all at once. And when we do k things all at once, we're just going to, each of the k things, we're going to say, if one of them finds a solution, we found a solution. Okay, so if you have a lot of these things running in parallel, some of them might require just a very few steps. Instead of some of them then requiring a lot of steps before we restart, we're just going to run each of them a little bit. Okay, does that make sense? Sort of? Maybe? Okay, so we're going to run a whole lot of these in parallel. That's the story we're going to do. And then we can have another search, which is called beam search. It's like parallel search, but we're going to select the k best out of all of the neighbors. So instead of having each one running separately, we're going to select the k best of them. When k is 1, it's sort of greedy descent. So that's what we've seen before. It's just greedy descent. When k is infinity, we're going to select all. It's like breadth first search. We're going to start with some assignment, and we're just going to explore everything. But when the value of k is smaller, we're then going to let us choose some other values. We're going to choose maybe the best 10 or the best 100 values. We're going to explore all the time. So we're going to keep exploring lots of them. That's called beam search. Okay, so we're going to, and then we can do other things. Then we could do something called stochastic beam search. It's like beam search, but it probabilistically selects the best k individuals of the next generation. So instead of selecting the best 10, we're going to randomly select them. And the probability the neighbor is chosen is proportional to its heuristic value. The probability we actually choose a value is going to be proportional to its heuristic value. So it's a bit like sort of simulated annealing. It maintains diversity amongst the individuals, and it reflects the fitness of the individuals. This is inspired by asexual reproduction. So we have all of these things that are reproducing, and the top ones survive, and the other ones die off, is the idea. So as we change things, the top ones survive, and the other ones die off, and you have survival of the fittest. But the algorithm is essentially the same as what we've seen before. We just have k of them. We're just going to select, at random, we're going to select these individuals. Okay, so that's sort of a stochastic beam search. And then the other ones you end up with is genetic algorithms, which are sort of often said to be the second best way to solve every problem, because I don't know any problem where they're the best method, but they seem to be okay at all methods. So it's like stochastic beam search, but we can actually combine them to create offspring. And for each generation, what we're going to do is we're going to combine the different solutions together. So if we have a great big huge network, if we have a great big huge constraint network, it might be the case that some part of the solution is good in this area. So someone might have a really good solution for the first part of the week, but really bad for the second half of the week. And someone else, some other of these algorithms might have a really good solution to the second half of the week, but it doesn't quite fit with their solution to the first half. If only we could combine those two together. And that's what happens with genetic algorithms. So we're going to select pairs of individuals. We're going to perform what's called a crossover. We're going to form two offspring, just like in sexual reproduction. And then we're going to mutate some values. And we're going to stop again when you find a solution. So we're going to look at this constraint satisfaction. We might have a good solution to this. Some other individual might have a good solution by that. By random chance, they both get good solutions if we found it. By other random chances, they might both get really bad solutions if we get a die out. Okay, and then we could do, so individuals here is, you do this other operation we'll do is this called crossover, is given the two assignments, we're going to select this some value at random and we're going to flip them. So we're going to form two new assignments. So let you have diversity, and this is, right, and this is inspired by genetics, inspired by how your genes combine together to form new individuals. And people play forever on these things, but the idea is reasonably straightforward given this definition. So we're just having parts of this solution, parts of this solution. We're going to recombine them. Some of them die out, and some of them survive. Okay? Let's stop there. But what I wanted to do in this last half here was to sort of just to give you some other ideas of algorithms that people do. Okay? But there's sort of, in some sense, they're all the same sort of algorithms. You're just iteratively improving things. But there's just lots of variance, and people spend hours tinkering with them and trying to find a slightly better solution than other ones. We're going to do something different. All right. Any questions? All right. Thank you.